It's a pleasure for me to introduce an speaker, Professor Luiz Farah from Federal University of Minas Gerais. Luiz got the PhD at INPA in 2008 under the direction of Professor Felipe Linares. Luiz works in nonlinear dispersive equations. Luiz in 2008 com prizes, Prêmio Melhor Tesis Capes, Prêmio Professor Teófilo Gutierrez. It's a great pleasure for me to introduce Luiz was my advisor. So today, Luiz will be talking about the global well-posedness and scattering for the homogeneous nonlinear Schrödinger equation. Thank you very much for having accepted our invitation.
Okay, Carlos, thank you. Thank you for the presentation. So first of all, I want to thank the organizers, so Juan, Luis, Reginaldo, and Carlos, for the organization of this nice event, a different workshop, online version, but I think all the scientific committee did a great job, and I think all the conference are very nice. And thank you for inviting me and give me the opportunity to share a little bit of my work with you. Okay, so I'm going to talk about this variation of nonlinear Schrödinger equation that we call inhomogeneous nonlinear Schrödinger equation, and my goal is to show you some results about global well-posedness and asymptotic behavior of the solutions, the scattering of the solutions. Okay, so this is the summary of the talk. So I'll try to give you an introduction about this equation. So then mention some results about global well-posedness and blow-up in H1, right? And then give you some recent results about scattering in the radial and non-radial case. So this is a joint work with Carlos, Michael Cardoso, and Jason Murphy. Okay, let's see. So this is the equation that we are going to consider today. So if if you take b equals 0, right? So you don't have this term here, so you just have the classical nonlinear Schrödinger equation. But we are considered this as a generalization where we put some function here in front of the nonlinear time-dependent function in front of the nonlinearity, and then we modify a little bit the equation and try to get also try to see if this equation also obeys similar results that is already available for nonlinear, for the classical nonlinear Schrödinger equation. So we're trying to consider a generalized model. Okay, so this is nice. So it also has some applications in nonlinear optics. And the good thing is, like as Felipe said in his previous talk, so we are going to consider HS space, Sobolev spaces, which are given by this, well known, it's given by this norm. And for this equation, we also have the same scaling argument that if we consider a solution, then we can rescale the solution to also get a solution, and then we look for the best Sobolev index that also Felipe mentioned. The best Sobolev index is the index where we have that the norm, the HS dot norm, is invariant under this scaling, and then we just need this power here, choose S, such that this power here is 0, right? And if this is 0, which means that this is scaling invariant, the norm is scaling invariant, then we have that index, critical index. So S, the critical index for us will be n over 2 minus 2 minus b over 2s. That's why we consider the nonlinearity, the function that multiplies the nonlinearity to be these, also these expression here, because with this expression we can show that we have the scaling property, right? And then we are interested in the case where this critical index is between 0 and 1. So if this critical index is greater than 0, then we call the equation L2 supercritical. And if this critical index is below 1, then we call the equation H1 critical. So the intercritical case will be where we have both conditions here, right? And of course, you can rewrite this condition in terms of sigma. If S sigma is between 0 and 1, you can show that in this case the sigma, just compute here and take what is the condition that sigma must satisfy, and then you compute and get that sigma is between these two guys here. So 2 minus b over n and 2 minus b over n minus 2, right? And also, we also assume that b, for technical reasons, that b is less than the minimum between 2 and n. Of course, we don't want b to be very large, because if b, for example, if b is bigger than 2, then we have negative guys here, and we don't want this sigma to be negative, right? Sigma is the power in the nonlinearity here. So this is the point. Okay, very good. So as usual for dispersive equations, like zk that we just saw in the previous talk, and for this equation we also have some conservative quantities, right? So two conservative quantities are the mass, so there are two norms preserved for every t, and also the energy. So the energy is this relation, these two integrals here. So this is the some like the L2 norm of the gradient, and then this is some Lebesgue norm here, but with this new weight here, x to the power negative b, that comes from the nonlinearity. We change the nonlinearity. So here, one comment that we can make here, important comment that we will see in the future, is that is that we don't have momentum conservation for this equation unless b is 0, right? So if b is not 0, then we don't have this quantity, and this quantity is somehow useful for the INLS equation to obtain scattering results. So you showed that how to overcome this difficulty when we don't have this conservation available for the INLS equation, right? The homogeneous version. Very good. So so before we go on, we see that look. So we are interested in solutions in H1, right? So we are always in H1 in this talk, and we want to investigate if this quantity here, the energy, is well defined for functions in H1. So if you have a function H1, can you say that this integral here is finite if you have that ut is in H1? So this is the first question, right? And this is the question that I put it here, and this is the answer. It's a paper in 2015 where we prove a type of Gallardo-Nirenberg inequality for this quantity that appears in the energy, right? So we show that this can be estimated as a combination of the L2 norm of the gradient and the L2 norm of the solution. right? Because if you are in H1, you have these two quantities here are finite, these two norms here are finite, and then you need to bound this as a combination of these norms. And this is the nice result that we get, and we can also say something about this best constant. So we can say that the best constant for this type of inequality is related to solutions of this stationary problem here, right? It's a liquid problem. So Q here is the unique non-negative and radially symmetric solution for this equation. Okay, so this is the first point. So yes, the energy is well defined for solutions in H1. And some comments about this Gallardo-Neiberg type inequality here is that, well, it was proved by Weinstein in 1983 in dimension greater equal than 2, and in dimension 1 by Nagy in 1941, right? So this is for the INLS case where B is equals 0, right? So if you go to the INLS case, then this type of inequality was first considered by Genu, right, in 2012, right, in the N2 critical case, where sigma is 2 minus B over N. So here we are trying to extend this Genu result to the case, to the intercritical case, right, between 2 minus B over N and 2 minus B over N minus 2, where sigma is between these guys. And also the existence and uniqueness of this ground state solution here. So consider this equation here. So the existence and uniqueness of radial solutions was proved by these authors here. So Genu, Toland, and Yanagi, right? Very good. So then, what can we say about global oppose? Well, as I was asking Felipe last talk, so because in general, the local theory implies that if you start with a small data in H1, then you have global solutions, right? Then your solution is global. But can you say something about how small should be the data? And this is the trick here, because this is somehow related to this Gallardo-Neiberg inequality that I showed you before. So using this Gallardo-Neiberg type inequality for this model here, we prove that if you start with, you take an initial data in H1, right? So this is all the assumptions that we are in the intercritical regime, and then this is the critical Sobolev index, right? So this is the assumption of B, not very large. And then, okay, so what is the importance of this result? It says that if you start with initial data in H1, such that is small in some sense, what sense? If a combination of mass and energy is less than a combination of the mass and energy of Q, recall that Q is the unique positive and radial solution for that stationary equation. And also a combination of the L2 norm and the L2 norm of the gradient of the initial data is less than the same combination for Q, then we have global solutions. Your solutions is global in this setting, right? And the key tool to prove this is exactly the previous inequality, right? Where, sorry, is this previous inequality here, where we can characterize the best constant as a solution of this equation, right? So this is the global result, and what is some comments about this result? Okay, so for B equals 0, which is the classical INLS case, so this was proved in that two critical case by Weinstein, where in the same paper where he proved the existence of the best constants for some Gallardo-Neiberg inequality. And then this was generalized by Homer and Rudenko in 2008, where they consider the intercritical regime, right? So here is the L2 critical regime, and here is the intercritical regime. And for the INLS, for the inhomogeneous version that we are considering here, so this was considered by Genou in that paper in 2012 in the L2 critical case. So in some sense, what we are doing, what I'm showing to you now, is that we could generalize the result of Homer and Rudenko to the INLS setting in the intercritical regime. So that's what we did here. So now, what can you say about? Well, you can ask if this condition is sharp, right? So up to the equality here, we can say that this is sharp, because if you now start with initial data in H1, but we add an extra assumption here. This is sometimes we define this space as the Virial space. Sometimes we call it sigma, right? So we ask the initial data to be in H1 and also in this space sigma, where now the solution is also in L2 with some weight, right? And then if you have the same condition for the combination of mass and energy, right? This is the same condition that we had before in the global theorem. Then if you ask the opposite condition in the combination of the L2 norm of the gradient and the L2 norm of the solution, then you have blow up in finite time. So you cannot have global solutions at that point, right? So in some sense, the L2 norm of the gradient must go to plus infinity in finite time, right? So this is the result here. And then let me make some comments about this. So for the NLS equation, the classical Schrodinger equation, so if you are in the critical regime, so we have several results. We have the result of Glaser in 77, where they also consider H1 and the Virial space and negative energy, right? And also the result of Tsutsumi in 84. Then Ozawa and Tsutsumi, they show that it's possible to replace this condition here, that is the initial data in the Virial space. You can replace this condition by radial. So you just assume that it's radial instead of this condition here. And with negative energy, they also show that you have blow up in finite time. Then for the general case, so instead of consider negative energy, but considering this condition here in the energy, then this was proved by Homer and Rudenko in 2008, and they prove in both cases. Both cases that I mean is that you take initial data in H1, and you can assume that either it is in the Virial space or is radial, right? For dimension and greater or equal than 2. Then you can prove also blow up in finite time, right? So later, these results about this INLS result here. So this author here, Jim, he replaced the Virial assumption here that we have in the statement here. So he replaced this by radial, right? This is possible to do following the ideas introduced by Ogawa and Tsutsu. So he did that a little bit. Okay. So what is the main tool to prove this type of result here? So the main tool is what we call some Virial type quantities, right? Because what is this? It's somehow a very nice relation that we have that is closely related to the equation that we are considering. So for example, if you consider this quantity, that's why we assume the initial data to be in this space sigma. So then it means that for all t, it's also in sigma, and sigma means that this integral here is finite. So it makes sense to compute the derivative of this guy. So if you compute the derivative of this guy and use the relation that we have for the equation, you get this. So it's a very nice quantity here. Very good. And also, if we compute the second derivative, it's surprisingly, it's related to the energy. It's very well related to the energy and to normal gradient. So you have these very nice expressions for the first derivative and the second derivative of this quantity, this integral here, right? And this was obtained by Glassey back in 1977 for the classical INLS equation. And what we showed here is that these conditions or these relations also holds for this inhomogeneous equation that we are considering here. It's very nice, right? And these conditions show that very easily you can use this to show that if you have, for example, negative energy, then you have blow up in finite time, for example, right? Okay, because if, for example, you can see from 12, if you have negative energy, then the second derivative is strictly negative. If it's strictly negative, you integrate 2 times in time, and then you get a contradiction if your solution is global, you get a contradiction. So that's very standard. Very good. So now I want to explain to you some results about scattering for this equation. So we already have this global result that says that, for example, this one. So if we have initial data satisfying these 2 relations here, 7 and 8, then we already have global solutions. So can we say something about this global solution? Can you say something about the asymptotic behavior of these solutions? So this is the notion of scattering. What is scattering? Scattering means that if you already have a global solution, suppose that you already have a global solution in H1, for example, then we say that this solution scatters forward if there exists initial data in H1 such that in some sense this nonlinear solution behaves like the linear solutions, like a linear solution at infinity, right? So in other words, you can take a global solution H1, then you can select initial data in H1 and look for the linear evolution of this new initial data. And then you compare this linear evolution with the nonlinear evolution that you have. And then you compute the H1 norm and then show that this goes to 0 as time goes to infinity. So at infinity, the nonlinear solutions is essentially a linear solution. So that's the idea of scattering, right? So this is what we want to prove. We want to prove that all the global solutions scatter, at least for, well, the same argument, the same idea, you can say backward in time, right? If you just, what is backward? Backward means that you are taking t to the negative infinity, and then need to find a different initial data for your linear evolution, right? That's the end. This is backwards, right? If this is 0, then you say that this scatters backward in time. Okay, so this is the definition. So let me recall some results about this for the classical INLS equation, the case B equals 0. So it starts in the celebrated work of Koenig and Merli in 2006, where they prove this type of result in the H1 critical case, right? And for radial solutions in these dimensions. So then, then it was extended by Philippe and Vijan in 2010 for non-radial, in the non-radial case, and in Virial and Farah. And then also it was proved by Dodson that you can also consider the non-radial case in dimension, right? 2000, very recently, 2019. So for the intercritical regime, so this is the intercritical. For the INLS, so can ML consider this case, the H1 critical? Now for the intercritical case, we have these results, for example. So it was first considered by Homer and Rudenko in 2008, where they proved this kind of result for the radial 3D cubic INLS. So it's something in the intercritical, a specific equation in the intercritical range. So then for the same equation, 3D cubic, they, in a joint work with Ducaetz, they also show that you can use this argument to prove scattering for non-radial solutions, right? So first they consider radial, and then together with Ducaetz, they remove the radial assumption, right? And then this was extended by Fang, Shi, Kaznav, 2011, and also Guevara, 2014, for the non-radial case and for all dimensions, right? So for all the intercritical possible equations, they show that this kind of argument also works, or this kind of proof also works, not only in the 3D cubic case, but also for the general case. Very nice. So what is the main idea? Well, this was, what is the roadmap, right? As Carlos Koenig said in his book about this topic. So the roadmap to prove these results is the following strategy. So first, we consider some variational arguments. In particular, you prove some kind of energy trapping here. Then you use a concentration compact procedure, like with the use of a profound decomposition and stability theory to prove the existence of, so you assume by contradiction that you don't have the limit that you want, and then using this concentration compactness procedure, you can prove the existence of critical elements and also the compactness of these critical elements, right? So with these properties, we prove a rigidity theorem that says that these type of solutions cannot exist, okay? And this is somehow this rigidity theorem somehow uses these virial type identities that I showed you before, right? So let's recall the first result, or this is the second result for the INLS model regarding this scattering theory. So this is very recently in a joint work with Carlos. We proved that almost in the intercritical range, we can have scattering for all the global solutions. So recall that this means if U is in H1 and if 7 and 8 are satisfied, this means that we have global solutions. 7 and 8 are these conditions, are the conditions that imply global solutions, right? And then if we assume that it's radial, then we prove that under the same assumptions, we have scattering using this Koenig and Merli strategy, the roadmap that I just presented So some comments here is that this means that we almost get the solution in the entire intercritical range. Well, if n is greater than or equal than 4, then the upper bound here is exactly the upper bound that we have in the intercritical range. So for higher dimensions, we cover the entire intercritical regime. And also for n equals 2, this is also, well, this 2 star can be taken infinity, and then we also cover the intercritical range when n equals 2. So the only thing here is that in n equals 3, we don't cover all the intercritical regime, right? So that's the point here. So when n equals 3, the intercritical regime is, so you must get sigma up to 2 minus 2b. So our result is not optimal because we don't get up to this level. So we get only up to 3 halves, right? And also, this is the second result because also back in 2017, with Carlos, we proved the same type of theorem in the radial case. This is also radial. In the radial case, but for the 3D cubic, right? So the 3D cubic, this is the 3D cubic and radial for the INLS. So this is our first result, and then we generalize this result for the entire, almost the entire intercritical regime here, right? Very good. So what is the main, let me try now to give you some ideas of the proof. Okay, so how to treat this term x to the power negative b, right? So if you look at this term that appears in the nonlinearity, you cannot integrate this term in the entire space, right? Okay. For any b that you have, this function here is never L1 in space, right? But if you restrict this space, then you can get some integration, right? So if you are around the origin, so for every gamma that you satisfies this relation here, we have that this integral is finite over the set. And if you are integrating away from the origin, then you have that this integral is finite if now we have a different condition, the opposite condition. So using these facts, we are able to like find the correct admissible pairs and then the construction. So this is the construction. I'm not sure if we're going through all these details here. I think I will skip this part. Okay, so this is the functional spaces that we use, some admissible pairs, but I'll skip this. And then we first prove some kind of H1 criterion, which says that if a certain norm is bounded and that an infinity in time and H1 in space is also bounded, then you have a scattering H1, right? And then this is just the construction, right? So this is, I think we skip this part because we don't have too much time. How much time I have left, so Carlos?
7 minutes.
7, just 7. Okay, so very good. So the idea is that, so if we assume that your critical level is below the critical level that you want, you can construct a critical element, right, which in some sense has a good norm infinity, and also that if this set here, the flow of the solution is pre-compact in H1. So that's the idea. So using this stability theory and also this profile decomposition result, right? And the good thing is that under the radial assumption, you can set the translation parameter that you have in your profile decomposition. Then you don't have a translation parameter here. So, okay, so finally we need to implement the rigidity part, but the rigidity part comes from that nice virial quantities that I showed you before. So instead of considering x modulus of x to the power 2, we modify this function by this, right? And then we still have a good relation here. We can take the first derivative and also the second derivative. This is the quantity that we have if we take phi to be exactly x to the power modulus of x to the power 2. And then if you don't consider this, if you put this quantity here, this quantity, this function here has compact support. So because of that, you add some extra terms here that we call the error terms. But the good thing is that we can bound these guys here because we also have that the flow is pre-compact in H1, and then, well, this is very easy, right? The first derivative, well, this is in L infinity, this is in L2, this is also in L2, and then if we use, for example, Boulder inequality, we get this bound. And then using that the flow is pre-compact, we get a lower bound also. And this is a contradiction, just integrate and use the fundamental theorem calculus that you have. That's the idea of the proof. Of course, I'm hiding all the technical estimates that you need to prove to obtain this solution, right? This critical solution. Okay, so let me try to give you some ideas about the non-radial case. What is the difference in the non-radial case for the NLS? So for the NLS, if you go through the arguments of Ducaet's, Rudenko, and Fangishi and Guevara, they prove that this flow is not it's not just pre-compact. To prove that the flow is pre-compact, you need to put some translation here, depending on time. So without this, we cannot prove that the flow is pre-compact. The good thing is that under the radial assumption, you don't need to consider this guy because you can take this guy to be zero, right? That's the idea that we have in the radial case. So for the non-radial case, we need to control this guy that appears, right? So what is the strategy for the non-radial classical analysis? To control this guy, so Ducaet's, and Rudenko, they use the conservation of the momentum. So using the conservation of the momentum, they show that this x of t is little o of t. And then they can use the Virial argument to conclude the proof. So what is the problem here? The problem here is that for the INLS, we don't have a conservation of momentum. That's what I said in the beginning of the talk. So we need to come up with a different approach here. So what is the approach? So the idea is that, okay, so to construct the critical elements, we cannot solve the equation then translate because we don't have, because of this term, we don't have the equation is translation invariant anymore. So the idea is to construct scattering solutions associated to these shifts going to zero, right? So if we can prove that, then this implies that we can take this translation that appears in the definition of K to be zero. The set K to be zero, and then the same argument as before that I showed you before, the Virial argument completes the proof. So this is what Miao, Murphy, and Zhang did in the 3D cubic case, right? And Mikhail, Carlos, and Jason, we generalize this type of argument to the entire intercritical regime, right? So as before, right? Under the condition that we know that implies global solution, so this global solution also schedules, right? So the main proposition to get this result is this one, which says that okay, if you have that the translation parameter that appears in the profile and decomposition, if we have that this translation parameter goes to infinity, then you can construct a solution, right, with initial data like this that scatters in H1 and also obey very nice bounds, good norms bounds here, right? So that's the idea. This is essentially the proof. So this is the construction, but I don't think I think I don't have more time. Sorry. So we skip these parts. Okay. So thank you for coming, and thank you, Carlos, again for the invitation.
Thank you, Luis. Thank you for the excellent lecture and for accepting our invitation. Thank you, Luis.
Thank you, Carlos. Thank you again. Very nice conference. Congratulations.